Okay, so section 3 is kind of a whole new topic, but it does have um, parts that are consistent with trigonometry. So we're talking about vectors. And vectors are quantities that have both a value or a magnitude and a direction. So what you see on the screen here is a vector. And we call it vector PQ. And it has a direction which goes from P to Q. Now if it was going from Q to P, it would be vector QP. And we call the point in space here the initial point, and the one that it's going to is the terminal point. And we call this the tip and the tail because it looks like an arrow, and this would be the tail of the arrow and this would be the tip of the arrow. So now you can have, well, let me not get ahead of myself here. So as I just said, vectors have both a magnitude and a direction. Now two vectors are equivalent if they have the same direction and magnitude, so they don't have to have the same initial point and the same terminal point. But they do have to have the same length, and they have to be going in the same direction. So if I were to take this arrow and clone it and just move it around, this new vector here would be equivalent to this vector because it has the same length and it's pointing in the same direction. Now you'd have to have something it was pointing relative to. Typically you think of a horizontal line and then the angle between that horizontal line and, I'm trying to get this thing so it's horizontal. Okay, so we have that line which is horizontal. So we'll define this angle, but this is the angle that we're talking about. Now these are just some examples of where you use vectors. So this is what's called a statics problem. It's part of physics. It looks at how forces acting on a body cause it to move at a certain acceleration. So we see three force vectors. Here this is an electrical circuit, and they use vectors to represent the relationship between different kinds of electrical elements. And this is showing the collision between an object and a flat surface and two objects. And analyzing this, you also look at vectors. Okay, so that's some applications. Now in the textbook, vectors are represented by lowercase bold letters, usually as such, but since I'm going to be writing things, I can't write bold or italics, so we'll write vectors in the following manner. So we use a letter, usually a lowercase letter, to represent vectors. Or we could use two capital letters to represent the points that are the initial point and the terminal point. Now, the vector in standard form, I'm showing this vector v with this little hat, we call it a hat, is in standard form when the initial point is the origin and the final point is some other point. So these two vectors are actually, well, they're not equivalent to each other. So as I said earlier, a vector can be defined from the coordinates of the initial point and the terminal point. So if we plot these 2 points, the initial point is 1, 4. The final point is 7, 7. So what we're going to do is we're going to represent this vector ultimately by a pair of points, not points, but values, which are going to represent the x change and the y change in the variable from the beginning to the end of the vector. So what we would have is we would call this vector v, and it's going to, instead of using brackets or parentheses, we use these triangular type brackets. So that also represents a vector. And there are two coordinates in the vector, which are going to be the x change from the initial point to the final point, the terminal point. So if you look at the x values, you have 7 and 1. So the x component of the vector is 6, and 7 minus 4 is 3. So that is this vector. Now if I were to clone this vector, if I were to clone this and move it to standard position, you can see these both have the same length and the same direction. This one's in standard position. This one is not in standard position. When it's in standard position, the coordinates of the tip are the same as the values for the vector. Now, because if I draw a horizontal line and then a vertical line at this point that create this right triangle, I can use the Pythagorean theorem to show that the magnitude of the vector, which is the length of the vector, is just this side squared plus this side squared, take the square root. So this is the Pythagorean theorem. It's also the distance formula. And in this case, v sub x is this coordinate, this value, and v sub y is the second number. This means the x component of the v vector, and this is the y component of the v vector. So this, we would say this part here, the horizontal part of this right triangle, is the x component, and the vertical part is the y component. And this is the final vector, and the length of this vector is the hypotenuse of a right triangle. Okay. Now, there's a special kind of vector, which is called a unit vector. And the special thing about a unit vector, as the name implies, just like unit circles, is that it has a magnitude of 1. So the magnitude of the unit vector is 1, and the direction is the same as the regular vector. So usually you have, a lot of times you have a vector and a unit vector. And the unit vector has the same direction as the regular vector, but it's either shorter or longer, but the magnitude of the vector is 1. So let's say we have this vector v, which has components 6, 3. The unit vector, so we got using u is to stand for unit. The little hat means it's a vector, is equal to the x component, which is 6, divided by the magnitude, which we haven't calculated, but we will in just a second. And then the y component of the unit vector is 3 divided by whatever that magnitude is. So let's go ahead and calculate the magnitude. So you've got the magnitude, and that's what these two vertical lines mean. They mean the magnitude. So that's equal to the square root of v sub x squared plus v sub y squared. So that's 36 plus 9. That's 45. So the magnitude is the square root of 45. And therefore, the unit vector is 6 divided by the square root of 45. And the y component of the unit vector is 3 divided by the square root of 45. Now, we probably want to multiply and divide by the square root of 45, just like we've done before. So you'd have 6 times the square root of 45, 45, and 3 square root of 45 over 45. And just to prove that this is true, it gives you a unit vector. If you want to find the magnitude of the unit vector, you do the same procedure. You're going to take this one squared plus the second one squared. So that's the, and then take the square root of that. So if we square this, we square everything. So you got 36 times 45. So 6 squared is 36. 40, square root of 45 squared is 45. In the denominator we have 45 squared. Then we have 9 times 45 divided by 45 squared. And you can see that this is going to cancel out with one of the 45s. So you get 36 over 45 plus 9 over 45. So this cancels out with one of those, cancels out one of those. Then you have a common denominator, so you add them together, you get square root of 45 over 45, which is the square root of 1, which is 1. So that is the unit vector. But if I were to plot these two vectors, the unit vector and the regular vector, they would just look the same, except one would be longer than the other. So if I go back to my picture here and I plotted the unit vector, it would look like this, except it would be shorter. So this black vector would be the same, would be a length of 1 unit. This would be 1 unit. This one would be the square root of 45 units. So there's one thing about unit vectors is that vector v, let me use the hat notation here. So you've got vector v is equal to the magnitude of v times the unit vector v, u. And you can see what would happen is if I took the magnitude of v, which is the square root of 45, and I were to multiply it by the vector like this. One of the vector operations is if you multiply by a scalar, you multiply each component by the same amount. So if I took the square root of 45 times the square root of 45, that would give me 45. 45 would cancel out with the 45 in the denominator and just be left with this part. Same in the second part. The square root of 45 times the square root of 45 is 45 divided by 45. So you can see that is verified. Okay, so let's look at another example. What is the vector which has an initial point of 2, 2 and a terminal point of 7, 5? What is the unit vector in the same direction? So we'll call this is P, this is Q. So the vector PQ, I'll call it PQ, so this is another way of representing vectors, is going to be equal to the x-coordinate of Q minus the x-coordinate of P, 7 minus 2, comma, the y-coordinate of Q minus the y-coordinate of P. So you get 5, 3 as your PQ vector. So if you want to find a unit vector, first you need to find out the magnitude of PQ. So that's equal to the square root of 5 squared plus 3 squared, which is going to be equal to 25 plus 9, which is 34. So that's the magnitude of P. So the unit vector U is going to be equal to 5 divided by the square root of 34 and 3 divided by the square root of 34. And again, you would multiply and divide by the square root of 34 to get rid of the square root in the denominator. And so that would be your answer. Okay, now, so we've talked about a vector, how it's defined by its initial and terminal points, shown how to represent a vector by the x and y components of the vector. We've talked about how the vector having its tail at the origin is in standard position. Now there are other things we want to be able to do with vectors. One is to have a scalar multiplication of the vector and to add or subtract two vectors. And it turns out that vector subtraction is kind of like addition is adding, or subtraction is adding the additive inverse. So we do the same thing with respect to vectors concerned. So we've already kind of alluded to the scalar multiplication because we did that when we worked out to verify that the unit vector was actually 1 unit long. So scalar multiplication is multiplying a vector by a constant. And if the constant is positive, then the vector length will change, but the direction will remain the same. Now, if the constant is negative, then the vector length will also change, but the vector will change directions. So that's by multiplying by a negative sign. That's essentially how you subtract vectors. You change a subtraction into adding the negative of a vector. So here we have this vector 3, 2, which so it has an x-coordinate of 3 and a y-coordinate of 2. And I guess we're showing the vector here by this short version. This is a scalar a, which has just a value. It doesn't have a direction. So a is a scalar. So to do the multiplication, if we have a times vector v, which is the same as a times the vector in its coordinate form, and in this case the scalar is 3. So when you have a scalar, all you do is you multiply each term in the vector by 3. So we get 3 times 3, which is 9, and 3 times 2, which is 6. So these two vectors, if I were to plot them, have the same direction. I've slightly offset them so you could see that they're two separate vectors, but they have the same angle relative to the positive x-axis. And if I were to set one over the other for part of the span, you wouldn't be able to tell the difference. Now if I multiply by a negative number, what will happen is, here's the original vector. By multiplying by a negative number, in its standard position, the vector now goes the opposite direction. So here goes up to the right, here goes down to the left. And again, if we were to represent this particular operation, we have a times v, or negative 2 times 3, 2. So just like before, we multiply each component by negative 2. So you get negative 6 and negative 4. So this coordinate here would be negative 4, and this coordinate would be negative 6, whereas this coordinate would be 3, and this coordinate would be 2. So there's two things happening. The vector is getting longer, but it's also changing directions. So this is the basic concept. K, some constant k, times a vector u. This is not necessarily the unit vector. You take k times the x component and the y component to get you the final vector. Okay, so that's multiplying by the scalar. Then if we want to add or subtract vectors, there's two ways of doing it. There's there's actually three ways of doing it. One's graphically, and there's more than one way to do it analytically. But it's kind of like what we did with the complex numbers. If you remember complex numbers, let's say x equals a plus bi. What we did is we had imaginary parts and real parts. And if we added complex numbers together, we added the real parts together and we added the imaginary parts together. Well, we do the same thing here. When you add vectors together, you add the x components together and the y components together. So from an analytical standpoint, here's an example. We have vector u, which is just a vector, not the unit vector. U doesn't always have to be the unit vector. So you got vector u, which is 2, 3, has the x and y components. The vector v, 3, 1, x and y components. So if I wanted to add the two vectors together, all I do is add the two components together. So I'd have 2 plus 3, 3 plus 1. So that would be 5, 4. So that's the add. And when we add these two together, a lot of times we call the vector that you end up with, which is a single vector, we call that the resultant vector. Now if you're subtracting vectors, then you just subtract the components. So you have 2 minus 3, 3 minus 1. So that would be negative 1, 2. So that would be the difference. Now, you can also think of this as u plus the inverse of v, negative inverse of v. So the negative of vector v is the same as vector v, except the negative positive numbers become negative, and if there are any negative numbers, they would become positive. So here we'd have 2, which is u x component, plus negative 3. So I'm adding to the x component of negative v, and then you have 3 plus negative 1, and you get the same answer. So they're equivalent to each other. Subtracting one vector from another is like adding a vector and the additive inverse of the second vector. Now there's, in terms of graphically what you do, you can draw both vectors from the origin in standard position. So here's one vector, here's the other vector. And if you take this, either one of the vectors in standard position, and then you copy it over so that the tip of the first vector is coincident with the tail of the second vector. So here's the tail of the second vector. Those added together, and then going from the tail of the first vector to the tip of the second vector, this gives you the resultant vector. Or you could do it the other way. You could take this vector as your first vector, add the second vector tip to tail, and you can see that you get the same resultant vector. It doesn't matter. So the order of operation is not important, meaning which one we do first. U plus v equals v plus u. Now u minus v is not v minus u, but negative v plus u would be, equivalent. So that's the, if you only look at half of this, this would be what we'd call the tip to tail method. The other one is to create a parallelogram. So you start with your initial two vectors, and then you start with these two vectors, and then you create a parallelogram. So you have this side you duplicate, and this side you duplicate, and that creates a parallelogram, and the diagonal from the origin to the opposite side, the opposite angle, is the resultant vector. Now what we're doing here is we are changing the first vector into an x component and a y component, and we change the second vector into an x and y component, and then we add the x components to get the total distance. So this x component plus the x component from this vector is going to be the total x component of the resultant vector. So this was, we already just looked at this, but here's another example. If I have vector u and I add a vector v, if I go this way or if I go this way, if I do v and then u, you always end up with the same results. So it's independent of order of operation. And here's three vectors. So we've got we've got this vector. Let me move them all out of the way here. So we got this vector, and we've got this vector. So those are the three vectors. And it doesn't matter which one I do first. You just have, let's say we start with this one. So second vector, third vector, get the same. That's your resultant from the origin to the tip of the third vector. Now if I just start with this one as my first one, and then I do this one second, and then I do this one third, you can see I get the same result. So any order of operation works. So this is formally what we can say about the properties of vector addition and scalar multiplication. So here it's saying the order of operation is not important. Vector u plus vector v is the same as vector v plus vector u. Here it's saying that if you group these things, that it doesn't matter whether you add these two vectors first and then add the third vector. If you take the first vector and add it to the sum of the second two vectors. The third one says there's this thing called a zero vector, and a zero vector is 0, 0. So it has zero length and zero direction, really, because there's no direction to it. So if you take a vector and add the zero vector to it, you get the same. You have the same resulting vector. This doesn't affect direction at all. Now if you add a vector and its additive inverse, then you end up with the zero vector, because you're going to add the x components or subtract the x components, but since they're the same, they're going to go to 0. As far as scalar, if you take a scalar times a vector, so you multiply this out first to get another vector, and then you multiply by the second scalar, it's the same as multiplying the scalars together first and then multiplying by the vector. Here we have, you have the sum of two scalars times a vector. If you add these numbers together, say 3 plus 2 plus 3, 5 times vector u is the same as multiplying each vector. In this case, yeah, it's just you can multiply them by c and d separately and then add the vectors together. Likewise, if you have two vectors u and v and one scalar, you can either add the vectors together and then multiply by the scalar, or you can multiply by the scalars first and then add the vectors together. Now if you take the scalar 1, multiply by a vector, it's just like multiplying a number by 1, it doesn't change the value. If you take the scalar 1 and multiply by the vector u, you don't change the value or the direction. If you multiply the scalar 0 times a vector, you end up with the 0 vector. So this one actually has a direction and magnitude. By multiplying by 0, you end up with the 0 vector, which has no direction or magnitude, so you lose some information there. And then finally, if you have a scalar times a vector, the magnitude of this product is the same as taking the absolute value of the scalar multiplied by the magnitude of the vector. So this is magnitude. It's kind of like sort of like absolute value, because the magnitude is always positive, but it's using the Pythagorean theorem to come up with it. Whereas with the scalar, we don't really have we don't have to deal with the magnitude, because all it is magnitude. So that's kind of the theory behind that. Okay, so let's do some operations here of two vectors, u and v. So the first one is u plus v. And if we wanted to, we could call that a new vector. We don't have to, but we could call it vector w. And all we do is add the x components together and the y components together, and that'll give us a vector with an x component of 6 and a y component of 5. Now if you take vector v and subtract u and subtract vector v, which we could call vector z. You take the x component of the first vector and subtract the x component of the second vector. Take the x component of the first vector, subtract the x component of the y component of the second vector. So x components and y components, so you end up with -2, 1. 4 minus 2 minus negative 2 minus 4 is -2. 3 minus 2 is 1. So that is that, and then here we're multiplying the vectors by scalars, so we want to do that first. So 3 times u is we just multiply each one of these components by 3, so we get 6, 9. 2 times v is, so we take v and multiply by 2, so we get 8, 4. And 3u minus 2v, all we're going to do is subtract this from that. So you get 6 minus 8, 9 minus 4. And so that's -2, 5 is the resultant. So here we have both scalars and vectors. And we've kind of done this, but we're going to formalize it a little bit, is you can break up the components or the vector into what we call x components and y components. So I've got 3 vectors, two that are already broken up into components. So, and these are not all necessarily in standard position, they don't have to be. But you have some vector, some length, some direction. The x component, you just draw a horizontal line that starts at the tail and moves far enough to the right that if you draw a vertical line that it would intersect with the tip of the vector. So you can just draw a straight line here. So this is what we call the x component of vector v. This is the y component of vector v. Likewise here we got vector u going to the left and up. So we have a negative x component because it's going towards the negative x direction. And then we have a positive y component. So we've got one more here. So this one, the x component would be this, and the y component would be that. So if we give it a name, we can label it. So if we call this w, this would be w sub y, this would be w sub x. So all of these y components are positive because my arrow is pointing upward. And, you know, doing vector addition, if I add this vector to this vector, what I'm doing is I'm putting the tail of the y component coincided with the tip of the x component. And when you add those two vectors together in vector addition graphically, you end up with this point, and so the resultant vector w is from the origin to this point. So that's what we're saying here. If we have a vector w and it's the sum of two vectors, the way we get the resultant vector is to break the original vectors up into two components, to add the components together, and then take the resultant values and create this new vector w. So what we're doing here is break u and v into components. Then from here to here, we're adding components. So we add the x components together. And then here we're forming the resultant vector by taking these components of the resultant vector and putting them in as the coordinates of the vector w. So let's show how this works, how you do this graphically. So let's say we take the vector u, add it to the vector v, and we end up with a resultant vector right like that. So that's my resultant vector. Okay, so now let's move these out of the way. Now if we take the x components, so we have a positive x, a negative x component here, we have a positive x component there, so this little bit here is w sub x, so I'm taking w sub u sub x and adding to it v sub x. The same thing can be applied here. I can take the y component of, let's take the first vector here, so this is the y component of the first vector. And I add that to the y component of the second vector. And so these together, added together, w sub y. That's the y component. And then I could add the x component, the y component of the resultant vector to get the resultant vector. So this is my w vector, the one that goes like that. So you can see I can do it just as vectors, or I can break it up into the component, take the components of the vectors and add the components together. And you see those are, it's equivalent, an equivalent result. Okay, so we're going to work some example problems now. So what is the unit vector with the same direction as this vector u? So since I call this view, I'll give the unit vector another name. We'll call it v. So the unit vector is, you take the components of the vector, so you'll have the x component, which is -2, and you divide by that by the magnitude of the vector u, and then you have the y component of vector u divided by the magnitude of vector u. So you can see all we need to do is figure out what the magnitude is, and so the magnitude of a vector, which is just a number, it's a length, is you take the x component squared plus the y component squared, and you take the square root of that. So you're going to have the square root of 4 plus 9, or the square root of 13. So that is that's the magnitude of the vector. So the unit vector, which I'm calling vector v, in this case is going to be equal to -2 divided by the square root of 13, and the y component of the unit vector is -3 divided by the square root of 13. And if you multiply and divide each term by the square root of 13, you'll get -2 times the square root of 13 over 13, and -3 times the square root of 13 over 13. And if I take this squared plus that squared and add them together, I'll get 1. And the square root of 1 is 1. Okay, now we also have these things called unit vectors in the coordinate directions, and they have special letters that we use. So we use I to represent the unit vector in the x direction. So it has a unit, it has a length of 1 in the x direction and a length of 0 in the y direction. And you can see it drawn here. So this is a unit vector, the x direction unit vector. Now the j direction, or the y direction unit vector, we use j, and it looks like this. It's got a x coordinate of 0, or x value of 0, and a y value of 1, and it looks like that. And so what you can do is you can represent the components of the vector as constants or scalars times the unit vector. That's the whole purpose for doing this. This is used a lot in physics and engineering to represent vectors. Instead of representing the vector as some magnitude in a certain direction, we represent it as some quantity times the I unit vector, and plus some quantity times the j unit vector. So Any vector can be represented as a sum of unit vectors multiplied by the magnitudes of the x and y components of the vector. Okay, so what that means is the x component is 5 units. Now this x component is not a vector, it's a scalar, just a number. It doesn't have a direction. The same way with v sub y, has a 10. To make it into a vector type arrangement, you take v sub x and you multiply by the unit vector in the x direction, and then you take the y component and multiply by the j vector, unit vector in the y direction. And so this is another way of representing this vector. So here we have these angled brackets. This is the x component, this is the y component of the vector. And we can draw, based on that, we can draw a vector from the origin to some point out here, which would have 5 units in the x direction and 10 units in the y direction. What this represents, what's different about this representation is that we have, this represents a vector, whereas these represent distances, coordinates. And so we have a vector in the x direction 5 units long, that direction, and you have a vector in the y direction 10 units long in that direction. And when you add those two vectors together, you take the tail of the second vector and connect it to the tip of the first vector, and what that gives you is a resultant vector. It looks like that. So you can see they both give the same result. It's just a different way of representing vectors. Okay, now another way of representing the unit vector is to use what are called directional cosines, or directional angles, I guess I should say. There are things called directional cosines, but that's a different topic. So what I have here is I have a unit circle, and inside this circle I have a vector. And because the radius of the circle is 1, the length of this vector is 1. So all unit vectors are going to be somewhere around the perimeter of this circle. And we would represent this unit vector, or any vector, by just the coordinates of this tip of the vector in its standard position. Now, the x component is going to be equal to the x component of this unit vector. Because the magnitude is 1, then the x length is going to be the hypotenuse, 1 times the cosine of the angle theta, and the y component of the unit vector is going to be the hypotenuse 1 times the sine of the angle theta. So this is using directional angles, where this angle theta is defined relative to the positive x-axis. So this angle is going to be less than 90 degrees. If it's in the second quadrant, it'll be between 90 and 180 degrees. So this notation allows you to represent the unit vector in terms of the cosine and sine of this angle. So you can do it in this vector notation, or you can do it in this unit vector notation. And the theta is called the directional angle. And then so there's a directional angle associated with the unit vector. There's also a directional angle associated with the any vector. It's the angle between the positive x-axis and the actual vector in standard position. So let's look at a problem here. We have this point 4, 5. So this vector is not a unit vector. So what is for one thing, what is the angle theta? And So you can find the cosine of theta and the sine of theta just using the same techniques that we've done earlier. So if you remember the unit vector, we'll call this vector v. We'll call this u. This is the u vector, unit vector. This is the vector v. So the vector v, in this case, is just the regular vector, is 4, 5. The coordinates correspond to the components of the vector. The magnitude of vector v is going to be equal to the square root of 4 squared plus 5 squared, which is 25 plus 16, which is 41. So you get the square root of 41. So the unit vector is equal to 4 divided by the square root of 41, comma 5 divided by the square root of 41. Or we can do it in unit vector notation. It would be 4 divided by the square root of 41 times I plus 5 divided by the square root of 41 times j. And the cosine of theta is 4 divided by the square root of 41. You're like, when are you going to multiply and divide by the square root of 41? Well, I'm going to do it now just because I just thought of it now. And the sine of theta is going to be 5 divided by the square root of 41, or 5 times the square root of 41 over 41. So you could then use these coordinates on the unit circle, which these are not going to be the normal pi over 6, pi over 4, pi over 3 type things. So you'd have to use, you'd have to take the sine of these to find out which quadrant you're in, and then use the reference angle to figure out what the actual angle theta is. So here's another problem relating to it. So what is the directional angle for the vector below? So that's what we're talking about here. So one way is you could come up with a unit vector in this direction, but you can also just look at it as the same kind of situation as we had for the trig functions of any angle. We use these coordinates to calculate the sine and the cosine. So the sine is y over r. In this case, r is going to be equal to the square root of negative 3 squared plus 4 squared, which is the square root of 25, which is 5. So you get 4/5, and the cosine is negative 3/5. So from this, we know we're in the second quadrant because the sine is positive and the cosine is negative. Okay, so those two, so we know second quadrant solution. And then to find theta, we would find the reference angle. So what do we want to use as angle? We'll use theta. So the reference angle is we can either use the inverse sine of the absolute value of 4/5, or we could take the inverse cosine of the absolute value of negative 3/5. We're going to get the same answer either way. And we can do either the angle in radians or degrees, but let's do it in radians. So we're going to take the inverse sine of 4/5, and we'll get 53.13 degrees. So that's my reference angle. But in this case, I just have a second quadrant solution, and that is theta is equal to pi minus theta prime. So I get theta is equal to pi minus, well, I should have done this in radians, so I forgot to change my calculator over. So we take the inverse sine of 4/5. So that's 0.92729 radians, and divide by pi. So you get 0.295 pi. So theta is equal to pi minus the reference angle, 0.295 pi, and you get 0.705 pi. You can see that I've already written it onto the graph. So that's my answer. Or you could take theta is equal to 180 minus 53.13 degrees. So 100 minus 53.13 is 180 minus 53.13 is 126.87 degrees. So those are the same thing. So that's my directional angle. And it says, what are the ways of to represent this vector? Well, one way is to say the vector u is equal to negative 3i plus 4j. Another way to do it is to take the magnitude, which is 5, and multiply that by the directional angles. So you'd have this cosine of, so you'd have negative 3/5 comma 4/5. So how I've done this is I've broken it up into some magnitude times the unit vector. And you could also do it in ij. So you could have 5 times, and I notice I'm not using this angled bracket. I'm using just a regular curved bracket. If I represent this as negative 3/5 I plus 4/5 j. So the ij makes it into a vector. Here you have to use the angled brackets to represent a vector. Okay, so now we're going to do some word problems just to explain where we would use these kinds of things. So what we have is we have two forces, which are, one force is 45 pounds, one force is 60 pounds, and the resultant is 90 pounds. Now what they're asking us to do is find what is the angle between the two forces, and so the question is, which angle are we talking about? Because you got this angle. Here's force, let's say this is force 2, and this is force 1. You see force 2 is longer than force 1. This is the angle theta between the two forces. But if we draw kind of like a half of a parallelogram here, this diagonal will be the resultant. This will be one side, this will be the other. So what we're done, in this case, we're given the resultant length, that's one side of the triangle. This is the second side of the triangle, third side. So we're given 3 sides. And if you remember, that means that we use the law of cosines. And so we can calculate this angle here, we can calculate this angle there, or we can calculate the big angle. And also remember, if you have, you always want to solve for the biggest angle first. Okay, so that's the one that corresponds to opposite this 90-pound force. So you can use the law of cosines to do that. So this is the side opposite the angle alpha. So the cosine of angle alpha is equal to f1 squared plus f2 squared minus f sub r, the resultant squared, divided by 2 times f1 times f3. So let's do that. Cosine of alpha. Now, once we get alpha, theta is this angle here as well, because this is, since one of these forces we're having coincident with the positive x direction. So if I find alpha, then I know that theta is 180 minus alpha. Okay, so let's plug the numbers in here. 45 squared plus 60 squared minus 90 squared divided by 2 times 45 times 60. And what we'll get is that the cosine is negative, which means that it's going to be between 90 and 180 degrees. Okay, so 45 squared plus 60 squared minus 90 squared. That's negative 2,475. And then divide by those three terms, and you get negative 0.4583. So alpha is the inverse cosine of negative 0.4583. And I get, okay, I need to change that to degrees. Okay, I've done something wrong here. Let me change it to degrees. Inverse cosine of negative 0.45333333. So again, 116.96. 6 degrees, but theta is 180 minus alpha, because these two angles are supplementary. So I get 63.04 degrees. So that's your answer. So what did we do here? We just showed that you can take the sum of two vectors and create a triangle, not a right triangle, but a triangle. Now you could do it other ways. You know, that's not the only way that you can solve this problem, but that's the way they were looking for us to do. Okay, now we have three forces with magnitudes of 70 pounds, 40 pounds, and 60 pounds acting on an object at angles of negative 30, 45, and 135 degrees respectively with respect to the positive x-axis. Find the direction and magnitude of the resultant of these forces. So what we're going to do is we're going to use the component method to figure this out. So let's rearrange some things here. So that's the negative 30 one. This is the 135 degree one. And this is the 45 degree one. So F1 is at negative 30 degrees. This would be positive 30. This is negative 30. So the first, if we go counterclockwise around this axis, this one's 45 degrees. This one here is 135 degrees. And if we go all the way around here, you can either say that's negative 30 or you could say it's positive 330. So we've got three angles. And it turns out, for example, force 1, there's two components. There's F sub x and there's F sub y. F sub x is F1, F sub x1, another subscript, F1 times the cosine of 45 degrees, and F sub y1 is F1 times the sine of 45 degrees. And what F1 here, I guess I should put these little vertical things. It's the magnitude of the force. And we know the magnitude of F1 is 40 pounds. We know the magnitude of F2 is, wait a second, make sure we're doing this right here. F1 is negative 30. Yeah, I'm getting these numbers correct here. So we're going to call the one at negative 30 or 330 degrees. You get the same answer. 330. Okay, so that actually is 70 pounds. Okay, F2 is the second one, which is 40. And the magnitude of F3, vector F3, let's put little vectors on here, so other vectors. But the magnitude is a scalar, so this is 60 pounds. Okay. So those are the magnitudes. Then to find the components, you just take the magnitudes and multiply by the cosine and sine of the angles. So I'm going to just put a space here. So F sub x2 is F2, magnitude of F2. Let's put these vectors in here again. Times the cosine of 45 degrees. F sub y2 is the magnitude of F2 times the sine of 45 degrees. And then you do the same thing for F sub x3 is the magnitude of F3 times the cosine of 135 degrees, and F sub y3 is equal to the magnitude of F3 times the sine of 135 degrees. Make sure your calculator's in radians. Now, if we look at this F1, we should have a positive x component and a negative y component if everything's right. So we'll take F1, which is 70, times the cosine of 330. I've got to make sure I'm in degrees, which I am. So I get the x component is 60.6 pounds. And then if I take 70 times the sine of 330, I get negative 35 pounds. Then I take the second one, which is 40, F2 times the cosine of 45, which is 28.3 pounds. And it's going to be the same for the sine because the sine and cosine of 45 are the same. And then you take 60 pounds times the cosine 135, which is negative 42.4 pounds, and F sub y3, you take 60 times the sine of 135, which is going to be negative or positive 42.2 pounds. So those are the three components. So now what you do is you say the resultant vector, well, the x component of the resultant vector is going to be f sub x1 plus f sub x2 plus f sub x3. We got to make sure we keep the signs, so we're going to have positive 60.6, positive 28.3, minus 42.4. Put that in our calculator. We get 46.5 pounds. Then you take the y component. So you take f sub y1 plus f sub y2 plus f sub y3. So we go through here, you got negative 35 minus, this is negative or positive? That's positive. So plus 28.3 minus plus 42.4. So I'm just taking these three numbers. So negative 35 plus 28.3 plus 42.4. Oops, did something wrong with my calculator. I forgot to minus. Oh, forgot to put a decimal point in there. Okay, so I get 35.7. So that's those are the components of my resultant vector. So to find the magnitude of vector r, you just take the square root of r sub x squared plus r sub y squared. So we get the square root of 46.5 squared plus 35.7 squared. So put those in our calculator. And it should be, it's always bigger than the biggest value, but it depends upon how much different they are. So we get 58.6 pounds. So that's the magnitude. And the direction, so we have both a positive x component, positive y component. It's a little more in the x than the y, so it's going to be something like that. And the angle we're looking for here is theta. So we're in the first quadrant, so all we have to do to find theta is just take the inverse tangent of the ratio of these two. So in the first quadrant it's straightforward. If it's in the other quadrants, you got to think a little bit more about what's going on. So it's going to be, what you do is you take the ratio of r sub y divided by r sub x. So you get the inverse tangent of 35.7 divided by 46.5. Plug that in. Inverse tangent of 35.7 divided by 46.5. You get theta equals 37.5 degrees. And that's it for the lecture part. So go ahead and try your homework. You'll have things like finding the unit vector for a given vector, finding the sum and difference of vectors, the scalar multiple of vectors, taking a vector and put it into component form, adding or subtracting two vectors by finding the components. So that's kind of the kind of problems that you have in this particular section.